Oh, this one, yes. Yeah, I did read it quickly. Okay. Okay, it says you're designing a scoring algorithm for a new hit rhythm game. During a round of rhythm flow, there are points in time when when a light goes up on, and as soon as you see that, you're supposed to hit a button. And human reaction time is, it varies, and it'll accept it if it's within a few milliseconds of when the light went on. So if it's within 15 milliseconds, you get 7 points. If it's within 23, you get 6. If it's within 43, you get 4. And if it's within 102, you get 2 points. And your job is to do what?
To add the total of points
Yeah.
for a sequence of.
So you'll be given what that player did, and your job is to score them. That's it.
Yes.
Okay.
Not quite.
Not
It's you have the times when you're supposed to press the buttons,
Oh, yeah.
and you have the times when the person actually hit the
Correct.
buttons,
Yeah. Yeah.
and you're supposed to assign them so that like you map like certain of their button presses to the actual so that they score as high as possible.
Oh, I see. There may be very different ways to do it. Wow.
Yeah.
It's not always the first one goes with the next one.
I didn't come up with a solution that could do that. So.
Okay. Well, since I haven't looked at the problem, I will know.
That's
And the
why I
constraints
waste
are, you're told N is the number of button presses and M is the number of actual. Oh, I see, number of expect. So these are the number of light flashes, and this is the number of button presses.
Mm-hmm.
And both of these can be as big as 2,000. Then the next 10 lines contains a single integer. This is in milliseconds, and the number can be up to 10 to the 9. Fine. So you got N of those and M of those. That's it. Okay, anything else? So your output is a single integer that tells you the total number of points the player earns given a maximally generous scoring engine. All right, let's work through the 2 examples and see how it goes. So the light flashed 3 times. This person clicked 4 times. Light flashed at 100, 200, and 300. You got these 3. So the first one gets assigned to, I see. So you're saying you could assign this to 200 and this to 100? That's an option?
Yeah, I think so.
Okay. Right. Okay, so if you do it the naive way of 1, 2, 3, then you would get, what is the scoring thing now? 0 to 15 is 7. So if it goes up to 102, you get only 2. So the first one would get 2 points. The next one was 40, so you get 4 points. 2 plus 4 is 6. And the third one was how much? So if you do it the naive way, 323. So 23 then, right? 23 will give you 6. So this person would get 2 plus 4 plus 6 if we do it the naive way. That would be 12. And you're saying if I assign the second one to the first click, that would be a 7. And the first one for the previous click, that would be not even 2, it would be a 0, right? But it's still better than this plus this. So it's 7 plus 0 plus a 6. So that's 13. That's true, it's better. But the answer was something else.
I think it was 20.
It's 20.
Why is it 20? Oh, I missed the.
Yeah.
19.
You can
So
assign.
99 can't be assigned to anything. That simply has to be thrown away, right?
You can assign 99 to 100,
200.
and then the 201 to 200, and then the 320 to 300.
Is it?
So
Oh, it can be
It can be
before?
yeah.
It can be
Yeah.
before? Where does it go? Where did it say that? I thought it had to be after. Let me read it again. Accepts a button press a few milliseconds earlier or later than expected. Okay, fine. More accurate presses are worth more points. Got it. Okay, so in that case, I would. Yeah, in that case, this would be a 7 and a 7. This one would be a 6. So 14 plus 6 is 20. Okay, got it. But is there a situation where you would do a later one to a previous one? Like if the 99 had not been there, what would the answer be?
They do stipulate in the problem that like if you have like if you have a pair of one button press and one actual press, and you have another one like here and here, and these two are less than each other, then these two also have to be less than each other.
I'm not sure I followed that.
Yeah, the problem kind of did a.
Where is it saying that?
If you scroll up, it says. Let me see. Yeah, it's in that paragraph right there.
This one?
Yeah.
If one actual button press happens before another actual button press, and both button presses are matched with expected button presses, then the expected button press for the first must be strictly before, so they all have to go, they all have to be in the same order, that's what it says,
Something like that.
right?
I think so.
If your inputs are in order, let's assume that we have these in order, then those also should need to be in order, right? But both have to be in sorted order.
That's given.
Sorry?
That's given. They tell you that both.
No, I meant that the matchings, not the actual numbers.
I think so.
Whatever you match need to be in sorted order. That's really what that condition is saying. Let me read it again.
I'm pretty sure that's true. Yeah.
Sorry?
I think that's it.
Yeah, so that's why dynamic programming works. Otherwise, dynamic programming won't work.
Yeah.
In fact, that is the critical point for dynamic programming to be applicable here. To score the game, match each actual button press with that. So it says with the following restriction. If one, so let me now put this on. Let's use this as the whiteboard. So it says that if one actual button press happens, if this happens before the other one, let's say this is the timeline. Here's a button press, so this is time. This button press happened before that one. Then and both button presses are matched with expected button presses. So somewhere here are expected button presses. If this one is matched to, let's say we do this match.
Yeah.
What it says is that the first must be strictly before the expected button press for the second.
Yeah.
So if these are in this order, then these also have to be in that same order.
Yeah.
So therefore, they can't cross. If you think of this as time,
Yeah.
you can't have the edges crossing.
That's how I
That's
wanted.
really what it says.
Yeah.
That's why if you allow them to cross, you cannot use dynamic programming. Now it turns out that you can use dynamic programming. How many of you don't know what dynamic programming is? Okay,
I do know about
but you're not so sure.
Yeah, no, I'm not so familiar with that much.
Okay.
Yeah.
All right, fine. So so essentially what you do is you sort both the lists And here you're told it's already sorted, so you don't have to do anything about that. And then, so let's say you have, this is the timeline for doesn't matter which one, for the lights, and then you have let's say these are your lights. And they don't have to be the same number on both sides. Your job is to match them in such a way that you maximize the score. So in this case, it might be that, it might be that, it might be that. And the thing is that you're not, so you're not allowed to cross them like this. This is the one that's not allowed. So therefore, at best you could do that and that, or maybe not even that. Maybe you do this. And since there's some score for, well, yeah, it's possible that this is the best. And here, whatever the differences are, you just add them up and you score this. Now the question is, what is that best match? And for this, it turns out that you can use dynamic programming. So let me explain dynamic programming a little bit. Oh, you wanted to present this, no? You had some ideas of how to do this. Why don't you go ahead? Let me, you are using dynamic programming, I take it.
Yes.
Let me set this up, and then maybe I will let you explain it in more detail, okay? So in dynamic programming, what you do, the way I usually teach this in class is to apply first try and build a recursive solution for the problem, and then you can after that you can turn it into what's called as a non-recursive version, and then figure out how to solve it. So what does it mean to solve this problem recursively? Here's how one goes about it. You start with the first guy on this end. And use a different color. You start with the first one on this end. Now there are three possibilities. It either gets matched to the first guy on this other sorted list, right? Or it doesn't. Well, actually, there are two possibilities. Either it gets matched with the first one here, or it gets matched with something else further down, a little bit later, or it simply doesn't get matched with anything. These are your three possibilities. So it turns out that you don't have to write. Yeah. And so essentially what it says is that in order to solve the problem, so let's call the problem as best match. And the best match takes two lists. You have a list of timings for this side and a list of timings for this side. We'll call that L and R. And you have a number of elements on the L, on the list L, so let's call that L, and a number of elements for the second one, let's call that R. It turns out that the best match for this is there are, in fact, we'll simplify it to just two cases. One is that the first guy here gets matched with the first guy here, or that's not what is happening. So, so if that first one matches, so then essentially what you'll have is a score for matching L of 1 with R of 1, right? In fact, it's actually easier to start with the other end, but it's fine. For now, we'll just say L of 1 and R of 1. So whatever the score is of matching these two, plus, after that, you're left with everything else, and you solve the remainder problem. And that remainder problem is a recursive problem of best match, where you take L with the first item removed, R with the first item removed, L minus 1, and R minus 1. Okay? Or it's either this or what are the other possibilities? Well, it turns out that there are two possibilities now. If this and this are not being matched, it's possible that this guy is being matched with something further down in the list. It's also possible that this is not the one that's being matched, but this guy gets matched with something further down in the list. These are your two possibilities. So it turns out that it's either that or it's a best match where you drop the first item in L, keep the R, and now you have L minus 1 and R as the items. Or you do best match, I'm just going to abbreviate it now. L remains the same, you remove the first item in R, L is, count of L is that, and R minus 1 is that. So what it's saying is, one of these three has to be the right answer. And so here you get a plus, so whichever is the maximum, so you do a maximum of either this, or this, and that will solve the problem. And you can actually write the solution as a recursive solution and pretty much solve the problem. I'm gonna let you take over because I just wanted to set this up because this is how you do dynamic programming. In a dynamic programming, the first thing you do is to write down this kind of a recursive solution. And then, actually, you know what, let me rewrite this, but matching the last one instead of the first one. So either I could match L of n, sorry, not L of n. I'm going to remove this and call this L of L and R of R. So instead of matching the first ones, I'm going to start with the last one. So either I match these two, the last two. If I do, then I will have, I essentially take the same list. I don't have to do this now, it becomes just L and R. I'm taking the same list of values, except that I'm going to stop at L minus 1. I'm not going to take the last one, because that's already been matched. So it's either this, or it's this, or it's this. And it turns out that it essentially is the same approach, but it gives you a clean recursive solution. You can take essentially this formula that I wrote and turn it into a recursive program. Now, in order to turn this into a non-recursive program, it turns out that you need to use a table, because you have to keep a table of all the problems you've already solved and then use those. And so you're going to need a two-dimensional table, I assume. And so I'm going to let Jian explain how this can be solved with a table.
Yeah. So most of what Giri said is.
If you want, you can use the other screen. If you want to. Yeah.
So, yeah, most of what Giri said kind of holds. We have a recursive approach where we know that our current state of the recursion is just two integers, which can be taken to kind of interpret the number of elements that we have left in each array, something like this. And based on the recurrence relation.
Yeah, in fact, let me just add to what you're saying. Since L and R are the same in every recursive call, I can take that out because it's common to all of them. So I can just erase that part and it'll work just fine. Which is really what he's saying right now. Sorry,
So,
yeah.
if you look at the recurrence relation as just being like, if you look at your current state as just being, how many like integers in each of the arrays that you have left, then, it kind of looks like this. So you have the choice of pairing the two together, in which case, neither of them can be used anymore, so you have to move on to the, next two elements before it. And you can also do, this, which is you wait for something better down the left array,
Yeah.
and then you have this, which is, you look for something better down the right array. And using that recurrence relation, you can kind of keep drawing this decision tree like this. I'm not gonna draw the whole thing, but just some of it.
Anyway, you get a ternary tree, right, at every node.
Yeah. And, I mean, you can kind of see that that continues, I'm not gonna draw it out for that one, but, already at this level, we can kind of see that there's, some things that look a little similar. Like, for example, yeah, so for example, you see that these here are both, L minus two and R minus one.
Yeah.
And so, if you actually kept on drawing this, you would see that, both of these subtrees actually turn out to be exactly the same. And like Dr. Giri said, because they cannot cross, we know that, this graph actually, as it turns out, is going to be directed acyclic, which is what lets us kind of store the results of these, identical subtrees after we do all our recursion on it. And so for that, we can just use a DP table. And so, we could still compute it recursively. But if you did it just recursively and nothing else, it would time out, cause you're looking at, N and M for each equal to 2000. And already with just 3 levels, we already have a lot of nodes. And if you draw this to a height of 2000, there's gonna be probably a few billion nodes.
2000 to the power 3, essentially.
Yeah, so you're looking at like 8 billion nodes,
Right.
sort of, and that's gonna be too slow, cause I think the time limit was 1 second.
1
So, instead of just recalculating it every time, cause you're gonna see nodes like these where you've actually already seen the result before, you can just keep the DP table, which stores each of these integers on R, which tells you how many you have left in each array. And so you can kind of ask yourself before the recursion, you can say if dp of R has been evaluated, so we can say like not equal to null or something. So you can keep the table initially empty and then start updating it with values as you go. And so, if you see that it's not null, that means that you've already done all of this computation before. And we know that because it's directed acyclic, the answer doesn't depend on any of its ancestors, it's just gonna kind of, be independent. And so that way you can just say, we can just return what's already there. Otherwise, if we haven't seen it yet, then we can do the recurrence relation, which is considering what happens when we take both of these and match them.
Right.
Or if we choose to just wait for a better choice to come along, maybe
Yeah.
by moving L down and keeping R, or keeping L and then moving R down like this.
Mhm.
And your base case for this, because you need a base case, otherwise it's just gonna stack overflow, would just be if you have one button press here, and you have a bunch of button presses here, or if you have the opposite case where you have a bunch here and just this one here, then actually another way of looking at it instead is it could be that you've draw these control boxes. It could be that in either array, you've already exhausted all
If you
your
have
choices.
questions, stop him anytime and ask. Don't wait for things to get worse.
My question is, in the question they said those should be in the button and the time should be in order.
Correct.
So if first button matches with the third button and the second press, we can't match with the
You
top.
cannot match it with the second, so that's why you've already removed those. They're never going to be considered anymore.
Okay, so we decrease the size of array?
Yes, that's what this says, right? This is equivalent to decreasing the size of the array,
Ah, okay,
right? Which is what he's also doing.
okay. And we decrease L because the match.
So either you decrease from the right array or the left array, we don't know which one.
Okay, if
Okay.
match happens.
So it
then-
might, if a match happens, it's this case.
Okay.
And here you have to add the score. Here you don't get any added score, right? Because nothing is matched there.
Yeah, I haven't understood why we are decreasing the left thing. I understood why we decrease the right thing,
Uh-huh.
but I did not.
Sometimes it might be that you also have to, I can create an example where sometimes you may be dropping from the left and sometimes you may be dropping from the right. Other questions?
Yeah, I have one extra question. About the decision of the DP table.
How do you make that decision?
Well, no, it's
Why did we decide on the DP table?
Yeah.
So
I understand it's because you of course want to record it and basically look at it in constant time. But
Right.
is that to the array, right?
So I can answer that question. You understand this recursive solution, right? The moment you see this, you go and draw the tree just like he did. Whenever you see things that are repeated, sub-problems, these are problems that are being repeated.
Right, right.
Essentially, it's the same computation, no point in
Yeah, I
doing it
understand.
twice.
You're going to have a
So
bunch of time.
essentially, I'm gonna store the solution of this in an array if I want to. And then when I need it later, I just have to look it up. I don't have to resolve the problem.
Yes, I wanted to ask why we don't use a hash map instead of a.
Because hash maps are simply not done in, you can do it if you want. Hash maps will add an additional layer of complexity, of speed and complexity for your problems.
lookups with hash maps are a
Yeah.
little complicated because, I mean, in most cases, you're
Here I don't need any lookup, I know exactly where it is, it's an array. Why do I need a lookup? Whereas a hash map will go hash this thing and go find where it is and then solve the problem. Here I know directly where to go.
Here, your integers are small, so
Yeah.
your probability of running into collisions isn't that big here, but, with other DB problems.
Yeah, also, well, if it gives you n equals 2000, and there will be data sets like that, 2000 times 2000 will give you a fairly large table. And so you're talking about 4 million already. And so your hash maps are going to be definitely slower. When you can do an array lookup, absolutely nowhere, at no time should you be thinking about a hash map.
Yeah, because with arrays, it's gonna be constant time, but with a hash map, you're looking at a worst case of linear, for retrieving, and we can just do it in constant time if we use an array, so, that's why we would want to do that. Because if you have 3,000 layers, then there's gonna be a lot of nodes, and you could just use the array, you could just use these as array indices, because 2,000 is not like a huge number.
Yeah.
And so, back to my base case, the base cases would be if either of the left or the right is exhausted. Meaning, if we say that we ran out of button presses in the right, then there's no way that we can get any more points in this situation. So whenever one array is exhausted, you just return 0 pretty much, and the same goes here. And of course, also for the case where both arrays are exhausted. So in all of these cases, you just kind of return 0 because there's no more matches that you can perform. And so, that's probably something else that would have to go here. If, L less than or equal to 0, actually, yeah, if L is equal to 0, or R is equal to 0.
Return 0.
Return 0. And that's how you set up the solution.
So because this is a recursive solution, it needs a stopping condition, and that's a stopping condition.
You can also do this, like Giri said, or you can translate it to an iterative solution, where instead of starting from the answer that we want, we can start with the very simplest cases. So instead of recursively starting at the end and then working our way to the beginning, we can start with the small values of L and R, which we know answers for, and then slowly build our way up to the original query. And that's how the DB solution works, if I didn't miss anything.
Yeah. That makes sense? More questions? Making some sense? Okay. Time complexity? All these operations are constant time operations, and you're going to fill up an entire table. And there can be n times n entries, so that's your time complexity.
For the score, what do you mean by the max of the score and pass match?
No, I'm saying max of these three quantities.
Yeah.
I'm
what
doing
is
a
score and
max
pass?
of these three, sorry. I'm doing a max of all three of these. 1, 2, 3.
Oh, okay, I see.
So when you do the math, n times n is about 4 million, which passes easily in a second, so.
Yeah. Other questions? So this is a classic DP problem. You will see there are other problems of a similar kind. Maybe if you can do some sequence alignment problems or something like that.
Knapsack?
Text editing, not knapsack.
Not knapsack, okay.
I'm talking about finding, what do they call it, substrings. That's basically the same problem. I can give you.
Oh, like longest common subsequence?
Longest common subsequence.
Yeah. I
That
can.
was, the time complexity, right? But what about the space?
Yeah, so the space is exactly the same.
Yeah.
The space can't be more than the time complexity. So space complexity is exactly that because you have to store that table. And the table has n rows and n columns.
Mm-hmm.
Okay, okay. And don't we also have to consider for like each recursive call as part of it?
Right, so you can, that's why I said you can either write a recursive version or you can write a non-recursive version, and I'll write the non-recursive version next if you want. If you'd like to see it, I'd be happy to write it down for you. Yeah, you'd like to see it? Okay, let me do it here. So let me erase this whole thing. Are you okay with this? Can I erase this? Yes, yes?
Yeah.
In the recursive thing.
Yeah.
How do we decide which one to reduce?
Right, so the way you do that is you say if, you say that if this problem has been solved for L and R, then just return the answer. And I would be storing a table. So the way I do that is, let's assume my table is called DP. If DP L comma R is not null, then it means that I've solved this problem before. I've seen it before, I've solved it. If it is, then I'd say return DP L comma R. Otherwise, I will go through this. Okay. Else, well anyway, that's returned, so it's gone. Otherwise, I'm going to return the maximum of these three things. Okay, that's the simplest version of the solution, and this works fine. But as he pointed out, there's an overhead for recursion, and typically it's not the fastest version of the algorithm for DP. So let me write you a non-recursive version. Should I erase this or this? What do you think?
Probably what's on the left, maybe.
Sorry?
Maybe what's on this board here, the left.
Remove this?
Yeah.
You wanna keep this? Okay. So let me erase this screen. That's what you said, right?
Mm-hmm. Yeah.
All right. So the non-recursive version would look like this. It'll say, it'll say for I equals 1 to n, for j equals 1 to m. I'm going to initialize this dp. I will say dp of I comma j is, let's say it's 0. Okay, I initialize it to 0. And now I'm going to say the following. If if dp of I minus 1 j minus 1 plus the score of li and rj, if this quantity is bigger than the max of, well, I can say bigger than or equal to the max of dp of I comma j minus 1 and dp of I minus 1 comma j. And then I'm going to do the following. I'm going to say dp of ij equals that quantity. Else dp of I comma j equals that quantity. we finish this through, we would have all the answers, and then we just say return dp of L comma R, because that's where the final answer is. Okay. So both of these are inside the, it's a nested for loop. All of this is within the for loop, this is outside the for loop.
Yeah.
This is within the if statement, this is within the else statement. So this is the non-recursive version of what you have here. Cool. So the nice thing here is that you're never going to solve the same problem more than once. In fact, you're never going to encounter the same problem more than once. And when you encounter a subproblem, you will only use subproblems that you've previously solved. Because dp of I minus one, j minus one, dp of I minus one, I of j minus one and I minus one j have all three been previously solved. And so the answers are already there. Okay. So all you have to do is to type this in on Saturday and try it. Or tonight. So this is a classic DP problem. Shall we move on to something else? So clearly here you see the recursive calls. This guy calls that and that and that. Whereas here there's no recursion. All you have are two nested for loops. And within here, this is just a constant time computation. So therefore, this whole thing takes you order of n times n. And at the end of it, you'll have the right answer. You can apply it to the example we have in the paper, sorry, in the problem, and check whether this works correctly. Okay? All right. Everyone has this. Can I switch the screen? The right screen. I did not. It's not a built-in PC. What is DP? Does anyone know?
Display port.
Display more.
Just to display? DP this HTML.
Maybe the ones that you should be pressing are on the other side.
Oh, here?
The one that says PC, maybe that one?
It could be because,
Is your laptop on?
oh, that's a good question.
Yep.
Nothing on my screen here, no wonder. Yeah, it's here. Okay, good. Any other problems? So, could we go to Menger sponge? Menger sponge, where is that? Not this.
I think it's the one after this.
Sorry, one after that?
Yeah, it was problem J.
Oh, this one. Okay. All right, So the problem here says that you start with a cube. I think it's 1 by 1 by 1, right?
Yeah.
And then in each iteration, you roughly cut it into the number of pieces that you see here, which is 27, right? So the original cube gets cut into 27 pieces, and then you remove 1, 2, 3, 4, 5, 6, 7. You remove 7 of these subcubes. Then you can see that naturally there are some bunch of cubes that are left there. You recursively do that to each one of them. And again, and again, and again. Now, what is the problem? So this process creates what is called as a level L Menger sponge. There's a famous Menger's theorem from something called network flow, if you guys have ever seen this. But this is I assume this is level 0, this is level 1, this is level 2, this is level 3. In each one, you're removing some material out of this whatever this block was, and in the end you get something that looks like a sponge because you've hollowed it out. Now, what is the actual problem? The actual problem, you're given 7 integers. Let's keep that picture too. You're told the number of levels. So in this case it would be 3. In this case it would be 2, here it would be 1, there it would be 0. So you're told the number of levels. And then you're given x numerator, x denominator, y numerator, y denominator, z numerator, z denominator. That specifies a specific point somewhere in space. And your job is to figure out whether that point is going to be inside the material or it's going to be sitting in free space. Okay, so if you take a point right there, it's obviously going to be in free space because you've removed that part of the sponge. If it is somewhere here, well, it is going to be in the material. So even if it's on the surface, you say that it's in the material, otherwise it's in free space. Let's see the words that they use. So your output is a single integer, which is 1 if the point is in that sponge, otherwise it's a 0. That's all you need to know. Now, you're given, everything is given as an integer, there are no real numbers, but you're given x numerator and x denominator, which means this is your x coordinate, y numerator and y denominator, so that's your y coordinate, that's your z coordinate. So you know exactly where the point is, and your job is to figure out whether it's in the sponge or not. Now, what you need to know is that the original cube, let's see what the original cube information is. You're told that the original cube goes from, it goes from 0, 0, 0, all the way up to 1, 1, 1. Okay, so you've got, you start with 0, 0, that's the origin, in 1 in each direction, and whatever cube you get, that's your original sponge, that's that guy there. So that means each side is 1, right? So that's what you start with, and you'll be given some coordinate, and your job is to figure out whether it's in the sponge or not. But one thing you know for sure, if the numerator is ever bigger than the denominator, what will happen? If in the input, if the numerator is ever bigger than the denominator, either in x or y or z, what do you know?
You're outside.
We're outside.
It's going to be outside because numerator divided by denominator will give you a number that is bigger than 1, right? If numerator is bigger. So therefore it'll be out of the sponge, forget about it, that's the easy part. Now, our job is to worry about things that were originally in the, or that were in the original sponge, but now we've removed L times, lots of material, so we don't know if that point is still in there. That's what you have to figure out, okay? Everyone clear about the problem? So let's do some examples, because then that'll give us some idea of, as to how to approach this. I'm gonna clear the screen. Okay. So let's do the first example. First example says, wow, L is 1,000, is it?
Yeah.
Yeah.
L is 1,000, fine,
That's when you
whatever.
know.
L is 1,000, and the point that you're worried about, or that you're being asked about, is 1/3, 1/3, 1/3. Okay. Now, maybe we'll do the easier one first, because
You can.
here the answer is easy, but we have to kind of go through the arguments. Let me show you a process, and then if you want, you can apply it to 1,000 and come up with the answer reasonably easily. So let me do the second example first. The second example says L is equal to 2, and your numbers are 49 divided by 81, 5 divided by 6, and 20 divided by 81. One good thing is that your x, y, and z are all symmetric in every respect. Okay, so if this thing is in the material, if it is in the sponge, if the point is in the sponge, it doesn't matter whether you flip the x coordinate with the y coordinate or the z coordinate. So it's enough to think about this in terms of one dimension, and you can solve each of the 3 dimensions separately. At least that's how I think about this. Fine? So therefore, let's forget about the 3-dimensional case. Let's just look at one dimension. Here is 0, here is 1. Right? After the first cut, what happens?
It gets cut in thirds.
So the middle third goes away. This goes away, removed. And you have 2 existing pieces. So that's after L equals 1. After L equals 2, each of those 2 remaining pieces will lose the middle third. So you'll lose that in the second round. Actually, let me. Okay, good. Let me use that. Oof. That's what you lose after the first cut. After the second cut, you'll lose that, and you'll lose that, right? And then after the third one, you're gonna lose a third of this guy here, you're gonna lose a third of this guy here, a third of this guy here, and a third of this guy. Is that clear? This is what happens along the x-axis. Now, if we can solve it for this 1-dimensional case, we can solve it for the 3-dimensional case, because all 3 things have to be in the material in order for the answer to be yes. Is that clear? Okay. Right. So let's just focus on the x coordinate. We won't care about anything else. So let's say we focus on, actually let's make this easy. Let's focus on the y coordinate, because they're all the same for us. So let's see what happens with 5/6 when L is equal to 2. Now, what we can do is when L is equal to 2, by the way, if I start with 0, I have 0 to 1. When L is equal to 1, the points of interest are 0, 1/3, 2/3, and 1. Right? 1 I can write it as 3/3. Right? When L is equal to 2, my points of interest where something interesting is happening is going to be 0.
1/6.
Sorry?
1/6.
1 by. What's the first point of interest here?
9.
That's right. So it's going to be 1/9, 2/9, then you'll have 3/9, right? Did I get that wrong?
Yeah, 1/3.
Yeah, 3/9 is 1/3.
Yeah, and then you're not gonna have 4, 5, or 6, and then you'll have 7, 8, 9.
That's right. So this is going to be 2/9. This is going to be 3/9.
And you don't have 4, 5, or 6.
And all of this is blanked out already. So this goes to 6/9. Then you will have 7/9, 8/9, and 9/9. Is that clear? So what I'm going to do is I'm going to get rid of the denominator so that life becomes easy for me. Okay? In order to get rid of the denominator, here I have to multiply it by 3. Here I have to multiply it by 9, which is 3 squared. So anywhere else, I'm going to multiply it by 3 to the power L. Is that clear? So that tells me what the numbers are going to be, and it'll help me figure out a lot easily. So therefore, this number, since L is equal to 2, I'm really interested in 5/6 multiplied by 3 squared, which is 9. Is that clear? It still doesn't totally get rid of the denominator, but it does help a little bit. So really, this number is 3, 2, so that's going to be 15/2. Is that clear? So we want to know whether 15/2, which is 7.5, is in our it's part of the sponge or not. And remember, since we multiplied everything by 9, my numbers now have been modified to 0, 1, 2, 3, 6, 7, 8, and 9, because I multiplied everything by 9. Is that clear? So therefore, all I have to do is to figure out, remember, this part is gone, this part is gone, this part is gone. Okay? So therefore, I'm looking at 7.5, and 7.5 falls right there, and it's not there. So it's a 0. So therefore, at least in one direction it fails. And that's enough to say it's going to fail, because it's not part of any material. Is that clear? Is that correct?
I think it was a 1, right? In the example. Yeah, it's 1.
So wait, so it has to be 0 on all of them in order to be 0, is it? Yeah. Oh, I see. So it may be 0 or 1 in different directions.
I think you maybe can have a 0 on one of them, because you can do on just like 2
Right,
edges
right,
and not a
right,
third.
Hold on a second. So I'm messing this up. Oh, right. I can't do this independently. I can't do it in 3 different directions separately. Okay, I have to put them together. Right. The reason is that if you go back to this picture, you'll see that what I said was wrong, and that's because if I'm somewhere here in this block, it's going to say it's part of the middle block, and so therefore in this direction it's chopped. And, but it's actually part of the, it's in the spine, so therefore what I said was wrong. So I have to do a little bit more.
Couldn't we check the other ones to see if the first?
Yeah, no, we will.
Yeah.
I'm just trying to see, if there's a simpler way of dealing with this. Yeah. Anyway, I'm going to show you how to independently figure out for each one of these X, Y, and Z, and then we'll see whether it's in the material or not. Okay. So for sure, if you only look at the X direction, then it says that we are here. That's L equals 2, and it's in one of the so if this is the X direction. It says that it's either in this part, or well actually in this entire part, or in that part. So that's really what it's telling you. So 7.5 actually falls right there. So therefore it's somewhere in this plane. Now we have to figure out what's happening in this plane and redo the calculations for Y and Z. So the question is how do I have to change this now? Good. So what we figured out in here, I haven't completely figured this out, but we know that it's in this portion, right? So if it's in that portion, that's the same as that portion here. So along the X direction, it's right here. Now we have to figure out what happens in the Y and Z direction. Actually, we did the Y direction, so Y could be along that, but we can think of this as the X, and it would be quite fine. Next, we should look at the X, that would be around here, and then the Z would go into the board. Fine? So for X, what we figured out was, for this one here, we figured out that it's not in the material. All right? Or it's in a portion where some chopping has happened, is going to happen, or would have happened. Let's look at this one here, 49 over 81. If we're looking at 49 over 81, and since L is equal to 2, we're going to multiply this by 9, and we're going to get 49 over 9. Now, what is that going to be? That's going to be somewhere between 5 and 6. Yeah. Right? So 5 and 6 means it's in this region.
It's awesome.
Right? So that also says it's a 0. So that therefore this also is going to come out as X. Great. So now we are in this region, and then we're doing between 5 and 6, so it's somewhere there. But now we're going to go into the Z direction and see what happens. Is there any portion of Z that will be between 5 and 6? Oh, 5 and 6 is actually yes, because it's not a no, this is wrong. This is actually a yes, because remember, didn't quite work that out.
I'm not sure which of the two is wrong, but the way we're adding it up, we were gonna say that it's not, but she's right, this is supposed to be one.
Yeah.
Yes.
No, that's correct, yeah. No, all I'm saying is that some material was lost in this interval. Here, if we go about it the right way, the material would not have been lost. But there's got to be an easier way to approach this. So do you have a quick description of the method that you guys used?
I made a loop for each it wasn't my idea, but it was a loop for each level. And so then it reads in the like A, B, C through F and makes into the X, Y, Z. And then it does a comparison for X, Y, and Z if they're between 1/3 and 2/3. And that's how I was understanding is like splitting each face into the
I see, so you do it one level at a time, okay.
Yes.
Mhm.
And then for the
I see.
multiplying each one by 3,
Yeah.
it multiplied it by 3 and then took the remainder of dividing it by B.
Yeah. So if we do that, then let's see. So first we go to L equals 1 and we ask the question, is that material there or not for this guy, right? If L is equal to 1, then we're asking if it is, so for L equals 1, we know that,
It should be a 3 by 3.
there should be a 3 by 3 here, and it's this part that gets removed in the outer one, but if you're in the middle one, it's actually, there's more that's lost, and then.
Each face looks like that. and
Each
then
face
it
looks like that, but the middle face actually looks a little different, right?
I don't think so. I think every face looks like that, and then because there's a middle piece. 'cause you can-
Every face looks like that, but I'm saying
You
if
mean
if I think of it as.
the cross
as
section?
The complete
As
center
the
is all-
slab, then that slab looks a little different.
If you look at the
Right.
cross section, you
If
have
you look at
like
the cross section,
this that's missing.
the first cross section looks like this, but the second cross section actually looks like this. Not only is this gone, but also this and this, and this, and this. This is the middle cross section,
Yeah.
right?
Yes.
You're not happy with this?
No, I don't think so. I don't think that's the way that the manager explained
So,
at the next level. The way that it's
So
empty.
what I'm saying is the following, here's the slab that I'm looking at, that's the first slab. Then beyond that is the second slab, that's this guy here. The third slab,
Yeah.
right?
That I agree with. Yes, yeah. I
So
see.
this is
Oh,
the
wait.
first slab, this is
Yeah,
the
yeah.
second slab, and the third slab looks like the first
No,
slab.
now I get what you're saying. Yes, yeah, I agree.
Okay, so that's all we're saying. So depending on which slab you're in, you have to use different considerations, that's all. Right? So now, let's say we look at the Z slab, this is the first of the Z slabs, this is the second of the Z slabs, this is the third of the Z slabs. So which slab did this fall under? This is 20/81, it's less than a third, so therefore, we know that it's the first slab that's here. So this is what gets applied, and then we are looking at the Y direction. Y direction is we said we'll go this way, so it's 5/6, which means it'll put it in the last one, so therefore, so first of all, this is in the first slab, then this is in the third slab, right, because it's 5/6. so therefore it'll come over here, 5 over 6 will come over here, right? So therefore here, it looks like the material so far is still holding up. And then we'll look at 49 over 81, and that would be in the middle slab. And so therefore, in the X direction, in this direction, it's in the middle slab. So therefore, that'll put us under somewhere here. I should use a different color. Yeah, it'll be somewhere here. Does that make sense? Along the X direction, if we call this as X, we're in the oh, it should be here. Let me see, it's either here or here. If we're looking at the X direction, if this is X, then it's in the middle portion. If you're looking at the Y, it's in the third portion, so that's over here. So that's Y, so it's in this third portion. And if you're looking at Z, it's in the first portion, so it would be in this block right there. Does that make sense? So what I've done is the following. I've taken this number, and I've figured out whether it's in the first third, second third, or the third third for each of the directions. And I'm calling this is X, this is Y, and that as Z. Okay? So I'm looking at X, 49 over 81 is in the middle section. So therefore, it falls over here. So it's somewhere here. Then Y coordinate is 5 over 6, which is in the third portion. So that's over here. So it's in here and in there, so that puts it somewhere there. But it could be anywhere in the Z direction. It could be, in fact, anywhere along this. And so now we look at the Z, it says 20 over 81, that puts it in the first third, and so therefore it's right here in this block. Is that clear? And that is allowed. There may be a simpler formula to figure this out, but this is one way to go level by level. And now that you come here, what you do is you subtract out some portions and then focus on just that part. And what you would subtract out would be, if it's 49 over 81, so then after you've checked out L equals 1, to do L equals 2, what I'm going to do is I'm going to do 49 over 81 minus 1/3. So remember, this is in the first one, so I don't have to, no, sorry, X was in the middle one, so I'm going to subtract out 1/3. So now I know I'm in the middle portion, all right? This will give me a number between 0 and 1/3. And I'm going to multiply this whole thing by 3, so that all the numbers are now in the range, they're in the range 0 to 1, right? And then this is the x-axis. The y-axis, I'm going to do 5 over 6. Remember, it's along the y direction, it's in the third one, so I'm going to subtract 2/3 now, and then multiply by 3. Okay? So that's going to now reduce the problem to that slab, and then the z, I'm going to do a similar thing. This time I'm going to do 20 over 81 minus 0 multiplied by 3. So this will be my new coordinates for the next level. And essentially I do the same calculations as before. The new coordinates are going to be now, the new coordinates are going to be, remove 27, that would be 22, sorry. 22 over 9. That's correct, yeah. 49 minus 27, that'll give me 22, and here it'll give me 9, right? And actually it's 22 divided by 81, then I multiply by 3 and that'll give me 22 divided by 9. Then I'm going to look at 5 over 6 minus 4 over 6, that's 1 over 6 multiplied by 3 will give me 1/2. And then here it'll give me 20 over 9. So now I'm going to repeat the same thing, except that I have one level less to worry about. So what I've done here, these are coordinates within within this block. Remember, this is a 1/3 by 1/3 block, right? Right? I'm only looking at that and I'm finding its coordinates in there, assuming that this is the origin. In order to find the coordinates, assuming that that's the origin, I have to subtract out 1/3 along the x-axis. I have to subtract 2/3 along the z-axis, y-axis, and 0 along the z-axis. That's what I've done there.
I was gonna ask about, because I was wondering if it mattered why you did the -0 from like the third term, because I was thinking about it from like the
Right,
bottom
so the
square
z-axis,
side.
I don't subtract anything because it's in the first slab. In the z direction, it's
Oh,
right there in
okay.
the first slab, so I have to subtract 0. If it's in the first slab, if it's in the second slab, I have to subtract out 1/3. If it's in the third slab, I subtract out 2/3. Because I need to move the origin to that point, right?
Okay.
So in order to move the origin from here to here, I'm going to go along x 1/3, along y 2/3, and nothing along the z. That's it. And so I've now reduced the problem to this. I will simply redo the same process. Essentially, I'll call the same process recursively if I want. So now I'm going to do for I equals 1 to L, which is the number of levels. Each time I have to do what I just did, but I have to do that algorithmically. Essentially, I have to figure out whether this is in the first third, second third, or the third third. And then after that, what do I do? Based on that, and based on my knowledge of what happens here, I will figure out whether it's in the sponge or not, because here I know exactly what happens to it. There may be a simple way to do that, and once I say yes, then I know how much I have to move the origin, and then I do that operation and then simply redo it. And I will repeat this L times. Is this roughly what you did? Yeah.
I think it's almost exactly what I did. Yeah.
Okay. And you were saying that solution is more elegant? Can you roughly describe it?
Yeah, because what I did was just kind of primitive. I broke it up into 27 subcubes like you did there.
Right.
And I just did the math to figure out. Basically, since I broke it into lattice points with the bottom left point being 0, 0, 0,
Yeah.
and the point all the way up there being 2, 2, 2. And then I just kind of did like a naive check to see if it was any one of the 7 deleted subcubes.
Yeah.
And if it was, then I would just exit
Right.
immediately saying 0.
No, but that's not what I'm asking. I'm asking, do you understand the
Yeah.
fancier solution?
Yeah, his solution just counts differently. So instead of just naively checking the 7 subcubes, it checks each coordinate to see if it's strictly between 1/3 and 2/3.
Mm-hmm.
And for each coordinate that satisfies that property, it adds 1 to a counter. And if that counter is greater than or equal to 2, then it's going to be one of the 7 deleted subcubes.
Okay, so let's see if that we can make sense out of that. So let's see, so I do this. So you're saying 2 out of 3? So at least 2, right?
Yeah.
So here I'll get x and y being one, so this would have a sum of three in fact. Sorry, you go from 1, 1 to 2, 2?
No, it's counting, like the middle parts, that is that third that's missing, so if, two of them are missing or more, then you know that it's off like two of the points, then it wouldn't be touching enough of like the size of the cube.
Didn't follow that.
For each coordinate, you, for each axis, you consider if it's between 1/3 and 2/3
Yeah.
Strictly, and for every time that happens, you add 1 to a counter.
Okay, got it.
And
Okay,
yeah.
got it. So here the answer would be 3. Here you would get, you would get.
It'd be,
2.
for that one, it should
Right.
be, for the bottom left one, it
So
should be
all these
0.
you'll get 2, these you'll get 2, this you'll get 3, 2, 2, 3, and here you'll get 1,
No.
is it?
Those numbers don't look great.
Sorry?
The bottom left should be 0. Cause it's,
Bottom left should be 0?
Yeah, only the middle cube would be a 2 on that one.
Oh, I see, I'm counting the other way around, I'm counting how many are surviving, okay, fine,
Yeah.
yeah, so it's 3 minus 3, fine. Doesn't really matter.
I see now whether you were doing it in the arrays, you just kind of flipped.
Yeah, just flipped it, that's fine, so you're saying here what, you want 0?
Zero
Yeah.
all the way around, just 2
So
in the middle.
0, here, 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 these should be 1, right?
Yeah, and then the middle one would be 2.
The middle one would be 2, because it lost material along the x-axis and along the.
At least 2 of the
At
axes.
least 2 of the axes, okay. And then here, this is the same, this guy will also be 1, right?
mm-hmm.
Yeah,
Yeah.
the same thing off of the
Well,
same level.
no, this one will become,
No, you're right.
2 now, because that's actually going to disappear, right?
No, you're right, this is
No,
all the
no.
same level,
That-
Yeah,
because this
you're
is
right.
all level 1.
Okay, this one is 1,
Yeah, and that's 1, 1.
okay? And now, the interesting thing is that this becomes 2, these are all zeros of course, because that's same as this cube. And then this one should become 2, right? Will it?
Mm-hmm.
Yeah.
And the
what
very,
about-
very middle one would be a 3.
The, right in the middle would be a 3. Okay, I get it, okay. got it.
Yeah.
Okay, alright, that seems like an easier way to figure out, sure. So that we could have done over here as well. We said that this is in the, middle cube, middle third, right? This is not in the middle third, this is not in the middle third. So only the first part was in the middle third, so therefore it's going to get a contribution of 1, right?
Think so.
According to you.
Yes. Yeah. Mhm.
So you get a contribution of 1 and so it survives.
Yeah, and so then you'd get a 1 return and that would be right.
Well, that's for L equals 1, then you have to repeat it for L equals 2.
Yes.
Oh, okay.
And for L equals 2, what do you have to do?
Well, but if that was L equals 2, then you'd still only have 1, and so then.
Yeah,
it's
for,
returning.
yeah, to apply it again, you
only have
just,
one of those that's in between like 1/3 and 2/3.
Sorry?
Because of those fractions, there's only one that's between 1/3 and 2/3. That one would be n equals 1 for this, and since n equals 1 is less than, or like, because it has to be n equals 2 or greater for it to return 0.
But you have to now try this one, right? Because don't you have to move the origin?
yeah, you have to translate and then dilate back up, so you're like zooming in on the surviving cube.
Correct, so
Yeah.
it's essentially getting you this.
Yeah, but
It
that's-
should get you this.
Oh, wait.
And here we're saying, something went wrong here.
Yeah, those numbers are greater than 1.
Those numbers are off, yeah.
Yeah.
So this should be 22, this should be 22 or 81. Yeah.
Not 66.
Sorry?
Not 66, because you multiplied it by 3.
Well, that 3, right. But if you multiply it by 3, you'll get
66. Because 49 minus 27 was, you said was 22, correct?
yes.
Yeah. So
Oh,
that,
but the 3 will cancel out this and you'll get 9 here.
22
I don't
and
think so.
27.
27, oh, right. What am I thinking? 9 I did my math wrong. Alright, fine. This is 27, yeah. And then this one,
1/2.
1/6 times, so it's 1/2, alright? And here,
27.
27.
yeah, and we'll see here that this guy is in the last third.
Mhm.
This is in the middle third. This is also in the last third. So therefore, contribution is one.
So
And
it'll return
so-
one.
So it'll return one in L equals 2. So we don't do L equals 2 unless L equals 1 has
Yeah.
supported it, right? That's what you're saying.
Yes, if
At
I don't.
each level, you're doing this, okay.
Yep.
Good, yeah. Yeah, now it sort of makes sense, what you just said. So in fact, if you start with this cube here, you can verify that even if you have if two of these say that material has been removed, then you're going to have the material removed, at least two.
Yeah.
It seems alright. Okay, let's stop here. Thank you. So,